Hello, so in this video we're going to look at exponential functions and this e to the x, okay, a letter e to the power of x, okay. Okay, so let's set the scene. So we're going to look at something called Bernoulli's problem. Hopefully I spelled that right. A problem, not theorem, problem. And it's something like this. So the question I'm going to ask is, if I start with £1, what I want to do is effectively, I want some compound interest. Okay, so if I have or receive, I should say, if I receive compound interest spread out equally, okay, or split evenly, okay. What is the most interest I can receive? So what do I mean by that is what I mean by split evenly. So for example, we could have you just get the interest all in one. Okay, so if I receive let's say I start with £1 and I get 100% interest in one go. Okay, 100% interest in one installment, right? So what that means is I get £1 and then I get 100% on top of that, right? So that'd be equal to £1, how much I get in total, and then 100% interest is 100% more, 100% on top of it. So it's going to be an extra £1, okay? So that'd be £2 then, right? Okay, then okay, now what if I'm going to do if I split up the installments into two? Okay, so that's going to be £1, and if I'm splitting this 100% interest, I'm going to split it in half, so that'd be 50% in two installments, right? So I get 50% more two times, okay? So that'd be £1, and what would happen is £1 and then I get 50% more, okay? So that would be 1.5, okay? That's my multiplier, right? Because that represents 50% more than £1. But that would be, but then I need to square it because it's two installments, because it's twice. I'm getting 50% on top of it twice. It's compound interest, right? Think back to GCSE. So if I work that out, I would get, after all, after I get the interest added on, 1 times 1.5 squared, that would be that'd be £2.25. Okay, so we get a bit more. Hopefully you notice if I split it in two goes instead of just all in one installment instead of two installments, I get a bit more. I get £2.25 compared to £2. Now again, let's split it even more. Let's say we have £1 and I have 25%. So each installment, and there's going to be 4 installments. What happens if I split it in 4, right? So I split the 100% interest in 4, so 25%, but in 4 installments, okay? So then that would be £1, and then obviously then I'd multiply that with my multiplier of 1.25. Remember, the 1.25 represents a 25% increase, okay? And that'd be 4 times, so that'd be to the power of 4. If I work that out, I get I get £2.44. Okay, so again, it's a bit more, right? 2.25, 2.44. So for example, this could be like, if it's in 4 installments, it could be like every 4 months in like in something like that, or every 3 months. Sorry, every 3 months in a year, right? Because obviously 3 months, 6 months, 9 months, and 12 months in 1 year, for example, right? So split it evenly. Then let's say in 12 installments, so it could be like every month. So let's say I have a start with £1, and then I want, I want in 12 installments. I'm going to split. I'm going to split it. I'm going to split 100% into 12. And so as a percentage, then this so obviously again we're doing 100% overall, but this 100% is again split into 12 times. So 100 over 12 is roughly 8.33%, right? So roughly then that would then be £1, and then I'd get 1.0833, and then that would be 12 times. So that's my interest added on 12 times. So if I do that, I get £2.61. Okay. So yeah. So you can notice that the interest I'm getting is actually more. So I get more money if I split it into more installments, right? But what do you notice with these four numbers? They're going up, right? We start with £2 and we end up with £2.61 if we split it 12 times instead of just doing it as a whole. But actually the increase is starting to go down. So initially we had £2 and we split it into halves. We get £2.25, 25% more, 25p more. Then 25 to 44, that is 19p more. So we've gone from 25% bonus, 25% more to 19% more. And then from £2.44 to £2.61, that's about 17%, 17p more. So what's happening is, if I get 25p more, then from then from 2 installments to 4 installments, I'm getting 19p more, and then actually from 4 installments to 12 installments, I get just 17p more. So the rate, or the actual increase, is going up. Obviously I'm getting more money, but the amount of extra money I'm getting is going down. It's gone from 25p to 19p to 17p. So actually it's starting to fizzle out. And actually then, if we then consider, let's consider splitting it into 375 installments. So now let's say we have £1, and we're going to split the percentage into 365 installments. So it could be like every day, right? So if I do that, then, well, what 100% split into 365, that is 0.27%, roughly, right? Roughly. So then the what I get from that, we start with £1, and then our interest is going to be 1.0027, right, to the power of 365, because again every installment, 365 installments, 365 payments. So if I do that, then I get £2.67. So actually you can notice the increase has really dropped off now. So from £2.61 to £2.67, that's only a 6p increase. So it's actually starting to fizzle out now. Hopefully you can spot, as I keep, I get more money overall. I get more money simply if I just split it into more installments. But it's starting to become less effective, right? So what happens then if I split it? What happens if I split it in general to £1 and n installments? Actually, no. Let's say we have £1, and then let's say we have a really big number. Let's say we have 1,000,000 installments, right? Let's say that, okay? So if I do 100%, so this again, 100% overall, 100%, 100 divided by a million is 0.0004%, 1%. Okay, so now not every time I'm getting that amount added on, so that would be £1 and 1.000 1.000, so many zeros, 0.00001, right, as a decimal, right? Yes, and then that'll be raised to a power of a million. If I do that, I get, oh no, so multiplied, there we are, so 1 multiplied by this, I then get £2.71 or 70. I'm gonna write the number out. 718. Okay, you can round it to 2.712. That's fine. P. So actually, roughly, when we have basically so many installments, absolutely tons, right? It starts to level out, right? From C, if we split it to 365 installments, and then we split it to a million, we've gone so much, right? From 365 to a million. Actually, the increase we get from £2.65 to £2.72, that's only 5p. So how it starts to really fizzle out, right? And actually, what happens is, if we keep splitting it into more and more installments, it actually just tends towards a certain number, right? Because then it starts to drop off. We don't get any more money, really. As we can see here, there starts to become a drop off point. And so actually, as we split the interest into infinitely many installments, we receive in total this number here. We get 2.718. Well, that's the same here, but then 2.7182818 blah 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 pounds, right? And I give it as a really large decimal. And so actually, this is E. We call this E. This number E, right? This is called E. Right, this number here, this 2.718. This is the long-term amount of money we get if we keep repeating this process of splitting my interest of 100% into infinitely many installments. We get this amount, we get this finite number, 2.718, this large decimal. This is called E, which is which you might hear it called Euler's constant. And so yeah, so then E effectively it's just this. It's this number here. You get 2.718281828. I got that from the calculator, right? And it's an ongoing decimal. It's an irrational number. Okay. So E is irrational, like pi. You can think of E as an infinite decimal, just like pi. Okay, they're both irrationals in this sense. So E is irrational. And yeah, and also on the calculator you can access E. So I've got a class Wiz, the sort of standard calculator. It should be near the answer button, where it says times 10 to the x. It's where you click your pi button. So pi is in yellow, E, the letter E is in red. And if you put that in your calculator, you should get this number here. Okay. So that's E, okay? Or generally we just say it's 2.718 usually to 3 decimal places, and usually that's what we mean by E. But yes, the calculator has it. But that is the number, okay? This sort of experiment leads us to find E, okay? With this process of splitting my interest into infinitely many amounts, so dividing it into infinitely many amounts. So I split up my 100%, but my 100% interest of £1, so we get 100%, but I split it into infinitely many installments, right? As you can see here, that is Bernoulli's problem. Okay, he wanted to investigate that, and that was the answer. So actually, the answer to this question is what the most interest I can receive if we repeat this in the long term. This is the amount you get, or £2.72p technically if you round it to pence. But that is the end number. That's the end result. Okay, so that's my answer. So that's E. Okay, that is E. You do not need to know any of that. All you need to know is E is this number here, and that is irrational. Okay. So that's where E comes from, this number here. Now, another very interesting thing about this and how it links to exponentials. Well, firstly, e to the x, right? So if we have f of x is e to the x, so that's e, which is this 2.718 to the power of x, right? It's just a number to the power of x. That's a type of exponential. And actually, the e to the x graph looks like an exponential graph, right? So we can draw the graph e to the x, and it will pass through 1, just like all the other exponential graphs. This is the graph y e to the x, okay? Just like any other exponential graph that we saw last time, okay? So that's the graph e to the x. Hopefully it shouldn't be too unfamiliar. That again, a sort of standard exponential graph. You do need to learn this graph. But it's just an exponential graph in general. But what's the most interesting about this is to do with its derivative. So we can actually differentiate e to the x, okay? So if f of x is equal to e to the x, then my problem is, what is the derivative? And to work that out, we can consider our first principles, right? If we don't know how to differentiate something, we could consider the first principles, right? What it means to differentiate. So remember in the differentiation chapter that if we got this function here, then the derivative we said is the limit as h goes to 0 of f of x plus h, take away f of x over h, right? That's my standard differentiation sort of definition, right? That's how we differentiate. So then if I take e to the x, then if I'm going to differentiate and use this sort of limit definition, this first principles, right? So then f of x plus h, if f of x is e to the x, then this will be e to the x plus h. Then take away f of x, take away e to the x over h, right? So hopefully with me there, I'm just applying this formula you should be familiar with from the differentiation chapter. That's first principles. We're just applying it to e to the x. And what we can do next is, actually, we can use power laws to split this up, because then e to the x plus h, we could say it's e to the x times e to the h. Because then if we've got the same base e, the same number, we can add the powers. Hence, what we've got, we can split this up. So then if we do that, that'd be e to the x, e to the h, right? Take away e to the x over h, and then we can factor an e to the x out, right? So then that would be e to the x of e to the h minus 1 over h. And actually at this point, we can actually take the e to the x out of the sort of limit, because the limit is only dependent on h, because that's what we're doing. We're just considering h. E to the x has no involvement in h, with h, so we can actually pull that out. Okay, you don't need to worry about that, but we can do that, right? So e to the x of limits h tends to 0 of e to the h minus 1 over h. So what we've got here is e to the x, and then we've got this, if I make it more clear, I've got e to the x multiplied by this whole limit here. How do I work that out? Well, that will require more advanced maths that you don't see, at least with the normal A-level course. But I'm still going to convince you what this limit is. So we're still going to work this out. I'm not going to do it, I guess, a proper way. Again, you to do it properly, more formally, algebraically, you'd have to look at more harder maths, which we won't do. But what we can actually do is just consider the graph e to the h minus 1 over h, which I conveniently drew down here. So I've plotted the graph e to the h minus 1 over h, so it's h against y. So what we want is the limit as h tends to 0 of e to the h minus 1 over h. So in other words, what happens to the graph e to the h minus 1 over h, which I've sketched here, as h goes to 0? So if h goes to 0, so it's going to be on the, well, obviously on the y-axis then. If h is 0, it's going to be here, right? Well, what do you notice then? Hopefully you notice as h goes to 0 of either end of the curve, on the before and after, it approaches 1. So that is it. So the limit is simply 1. It goes to 1. Now, I won't get too technical, but you might be thinking, well, if I plug in h is 0 into here, that would be e to the 0 take away 1 over 0. I can't divide by 0, right? That's fine. With limits, again, I'm not going to get too technical, but with limits, we only care about what happened. We only care about where it tends to, right? So either side of the curve, it tends to 1, but it doesn't matter if it's not defined at 0, right? I only care what a limit means by a limit, right? So what happens as the curve is pushed towards h is 0, not actually what happens at h is 0, but what happens when it is pushed towards it. So you can see from either side of the curve, right, from left and right, left and to the right, it goes to 1 either way. So again, I'm not going to get too technical, but hopefully you're convinced that this limit just goes to 1, as you can see with the graph. Okay, so that'd be e to the x times 1. Well, that's just e to the x. Well, then actually, that tells me that the derivative is just e to the x. It's the same thing, right? So the function is e to the x, and actually the derivative is also e to the x. And so that is, this leads on to the reason why we bother with e, is actually the special property is the derivative is the same as the original function, right? So if the function is e to the x, and the gradient is also e to the x. So the special property is, I'm going to note that with e to the x, with y equal e to the x, the gradient function is the same. So that means dy dx is also equal to e to the x, okay? And actually, e to the x is the only type of function that has that property. So when we want to set dy dx, the gradient to equal y, so the original function y equal to its gradient, then e to the x is the only sort of solution and the only candidate here. You'll see more when we look at differential equations in year 2. Again, I'm not going to try and be too detailed here, but that's it. We're technically a e to the x, a constant lots of e to the x, alright? Technically, that's the only type of function that where the gradient is the same as its original self, right? So a multiple of e to the x, okay? And it's a multiple because obviously with derivatives, for example, when we looked at differentiation, 2x to, let's say 2x squared, I can just ignore the 2. All the constants I just kind of ignore, and that would be 2 lots of, and then x squared would be 2x, which is 4x, right? So the constants don't matter, so I can add a constant on. But anyway, the idea is e to the x, the gradient, the derivative is the same, okay? And it's the only type of function where that is actually true. So it's quite a special result, actually. And so yeah, so that's the key thing you need to know, is if y is equal to e to the x, then the derivative is e to the x. And actually, another case you do need, another extension of this you need to know is if y is equal to e, but some multiple of x, so kx, then the derivative is actually k lots of e to the kx. So we bring the k to the front. Again, it's very, very reminiscent of when we had, say, x squared, where we had powers when we differentiated in the differentiation chapter. We brought the power to the front, so that will go to 2x. Okay, we knock one off. It's the same concept, pretty much. So the k in front, the number of x, comes to the front when we differentiate. And so that is the key result we will be using in this chapter. Okay, to see more clearly what, again, we will look at chain rule in year 13, in year 2. So I'm not going to explain it now, but you do need to know this result, okay, which we will look at some examples now. So that's really the main thing. You need to know this derivative here. I'm going to box, and you need to know the graph y is e to the x. Okay, you don't need to know any of the derivations or the stuff I've done or the background. You just need to know that the graph e to the x looks like this, like a bog standard exponential graph, and also the derivative of the exponential as well. Okay, you need to be able to differentiate. Okay, so I'm going to look at some examples now. So so we've introduced it. Okay, so now we need to know to use e. Okay, so we need to differentiate with respect to x. Y is e to the 4x. So if we differentiate it well, then the derivative, again, we have e to the 4x. So remember we just discussed, if y is e to the kx, then the derivative is k e to the kx. Well, actually here, k is 4. We've got a multiple 4. So that'd be 4 e to the 4x. Okay? Then for part B, we have y is e to the minus a half x. So again, then the derivative, we bring the minus a half to the front. So it'd be minus a half e to the minus a half x. Then part C, we have y is 3e to the 2x. So again, the 3 is a number outside, it's a constant, we don't bother with it, so it's still going to be 3. Then we have 2x. So the 2 is going to come to the front, so it's going to be 2e to the 2x. And then we can actually just expand to get 6e to the 2x. And there we are. So that's essentially differentiation, okay, using this rule here. Okay, again, we need to be able to sketch the graph e to the x and transform it as well. So again, make sure you're comfortable with graph transformations. So here we firstly need to sketch y is e to the 2x, where again, e to the x looks like this. Right? So that's e to the x at 1. Then what's e to the 2x? Well, again, if you consider functions, if f of x is equal to e to the x, then what's e to the 2x going to be? It's going to be f of 2x, right? Well, actually then, f of 2x, right, remember our graph transformations, what we do inside the function, we do the opposite to what we expect. What do we expect? We double the x coordinates. But actually, instead we're going to divide the x coordinates by 2. So we're going to divide x coordinates, or x values, by 2. Informally, right? That's essentially what we're going to be doing. Or multiplying by half. So then to sketch this then, if we're going to basically halve the x values then, but let's say x here is 2. Let's say x is 2 here. Then x, if we were to divide it by 2, it would be moving here at 1. Okay, so that'd be where the point would move to there. Then let's say we have the point here. Let's say this is 4. Then actually that would move to 2. Okay, that would move to 2 there, straight across. Then let's say with the point here at, let's say 8, but then that would move to 4. Okay, so now you can start to see where the points would, these new points here, they start to form a curve, right? And actually, this point here, the y-intercept at 1, that's a y-intercept, that's when x is 0. So half of 0 is still 0. So it stays where it is. Oh. So actually then, the graph sort of is squashed, right? If you consider what will happen to the x values. So it'd look a bit more like this. Okay, so it's a lot more steeper, essentially, because it's more squashed down compared to e to the x, right? And yeah, so that'd be y is e to the 2x, okay? And it'll still be at 1. Okay, y is 1 there. Cool. Then for part B, we now need to sketch 10e to the minus x. So what I suggest doing here is firstly, obviously we're going to sketch e to the x first, and then see what happens when we transform it. So e to the x again looks like that. So then firstly, I'm going to sketch e to the minus x, because then I can just multiply by 10 at the end. So e to the minus x first. As again, remember, when we transform functions, we need to change the x parts first. So anything inside the function, so in this case, anything affecting the x needs to be transformed first. Then anything affecting y outside the function, we change after. So that's the ordering, right? So firstly, e to the minus x. Well, think about it, that would be f of minus x, right? If e to the x is f of x, then f of minus x is e to the minus x. So that would be, again, if we use our philosophy, you could just simply remember that as reflection in y-axis. That's perfectly fine, but alternatively, you could then recognise what we do the opposite to what we expect. So again, what you'd expect is to multiply the x values by minus 1. Instead, we're going to divide by minus 1. But actually, that is the same thing in that case. Multiplying and dividing by minus 1 gets the same thing. So we're going to divide or multiply by the x values by minus 1. So if we take a point here, let's say this point here at 2, then that, if we multiply that by minus 1, it basically flips sign. So it goes to minus 2. Minus 2, and that'd be where the point moves to. Again, this point here then would then move to somewhere here, just simply across the y-axis, and then you can spot it will be indeed a reflection in the y-axis. And then let's say this point here would move somewhere there. So if I plot these 3 points, then the curve would look something like this if it's reflected, right? Okay, so that would be y is e to the minus x, and again that will still be 1 there, but there we are. Okay, now we don't want e to the minus x, we want 10 e to the minus x. So y is 10 e to the minus x. We then need to, because the 10 is outside the function, outside the e to the minus x, right? That affects the y value, so we're going to times the y values by 10. So that means then, well, this point here, this point 0, 1, y is 1, that's going to times 10 to get to 10. So the y-intercept will now be here. That's where the new y-intercept will be. And again, the y values, essentially, all of it times by 10. So the function gets larger, essentially. So it's a lot, so what happens is the graph is a lot more sort of steeper. So it looks something like that. Oh. Something like that. It's a lot more steeper. Hopefully you can recognise that. In fact, I'll make it probably even a bit more steeper, actually. There we are. Something like that, right? So it's a lot more steeper than, say, the previous graph, e to the minus x, okay? And the y-intercept is at 10. So that'd be y is 10 e to the minus x there. Okay, then part C, we need to sketch y is 3, add 4e to the half x. Okay, so firstly, okay, there's a lot of stuff going on here. So firstly, again we have e to the x. That'll help me visualize what to do to it. That's e to the x. So then, firstly, I'm going to want to sketch y is e to the half x. So again, that the half x affects the x inside the function. So that I'll do that first. So it's kind of like what I do inside the function, I do first, and outside I do last. Right? If that makes any sense. So half x then. Well, again, that would be f of a half x, right? If f of x was e to the x, and e to the half x would be f of half x. So what would we expect? We would expect to multiply the x values by 2, but actually we're going to divide them by multiply them by half. Sorry, but we're going to instead divide the x values by half. But actually, dividing by half is the same as multiplying by 2. So we're going to multiply x values by 2. That's what this is going to do effectively. Okay, effectively. So if I then do that, then if I multiply the x values by 2, so again this is e to the x. So let's take this point here. Let's say that's 2. That's then going to move to 4. Okay, that's going to stretch out there. That'd be my point. And then let's take another point. Let's take this point here. Let's say that's 3. That would move to 6. So that'd be over all the way over there. Okay. And then it's still going to pass through the y-intercept there at 0, 1. So actually, if you start to sort of visualize the graph we're going to get there, it's going to be less steeper, right? It's going to look a bit like this. Something like that. So that's going to be y is e to the half x, right? As you can see there. Okay, then we need well, again, if we're gonna work outwards, so we first did e to the half x, now we're gonna do 4 e to the half x. So y is e to the 4 e to the half x, and then so what we're gonna, it's outside the function, so it's gonna do the y values. We're gonna do what we expect, so we're gonna multiply the y values by 4. So that means, in relation to the previous graph here, if the y values are multiplied by 4, well, firstly, this one, this y-intercept at 1 will now be at 4. Okay, it will now move to 4. And Again, the same idea as the previous example when we had 10 e to the minus x. If we multiplied it by 10, it become a lot more steeper because the y values will become bigger. So it will look like this, and it become a bit steeper because again the values of the graph is just bigger in general, so it rises quicker, right? So it looks something like this. Okay. Okay, cool. So that'd be y is 4e to the half x. Then lastly, we then need to sketch not 4e to the half x, but 3 add 4e to the half x. So we need to add 3 on. Okay. So y is 3 add 4e to the half x. So actually the 3 is outside, so we do what we expect. What do we expect? We expect to add 3 to all the y values. So if we added 3 to every y value, the graph will just shift up by 3. So it's going to move up by 3. And actually, this is probably the easiest sort of transformation, because then we just shift the graph up by 3. A translation, right? So if we shift the graph up here by 3, it's just going to look like this. Oh. Yes, like this, okay, and the wind, and then it tends towards an asymptote. Well, actually, it's not going to tend to 0 anymore, is it? Right, it's not going to tend to 0. If I were to continue the graph on, it would tend to 0. But that's the asymptote. The asymptote was originally y 0, but then the asymptote, like with all the other parts of the graph, also move up by 3. So then this and this will be y is 3 add 4e to the half x. And actually, this 4 here, the y-intercept of 4, would also move up by 3. So then it'd be 7. Okay. And so yeah, that is what that is the graph there. And so okay, very tricky those are, I think, but there we are. Okay, let's have a look at some exercises. So we need to rearrange f of x e to the 3x add 2 into this form here. Okay, so what I notice is it's a multiple of a multiple lots of e. Okay. Well, actually, a very common technique this is actually recognised again. We can split up the powers in this way. So it's e to the 3x times e to the 2. That's a power law, right? That's saying a to the m times a to the n is a to the m add n. That's my power law, right? Again, need to be comfortable with power laws. They come up all the time. So we can split up the exponential in this way. And so actually, that is in the form here. If I were to compute e squared, so again, remember e is just a number 2.71. What was it? Yeah, 2.718, blah, blah, blah. That's e. It's just this number, right? Simply. So then e squared is going to be this squared. If I put that in the calculator, well, you can put e squared in the calculator, and you'd get 7.31389. So that would be 7.389 e to the 3x. Right? Obviously, it's an ongoing decimal, e to the 3x. So it is in this form here, okay? So a is technically e squared, right? But then this is 7.389. So let's say 3 decimal places. And b, well, then b, then we have a e to the bx. B is the 3 out the coefficient of x, right? So then b is 3. Okay, so it's in this form here. Okay, so again, if I was to do this to 3 decimal places, that would be approximate to 7.389 e to the 3x. Hopefully you can spot this is in the form a e to the bx. Now, if a is 7.389 and b is 3. Okay, right, then it says hence or otherwise sketch this graph here. Okay, so now we need to sketch the graph. Oh, I don't have much room here. Okay, I'm going to get rid of some of this. But I need to sketch the graph effectively. The graph y is 7.389 e to the 3x. Okay, I'll make a note of that there. Okay, so I'm going to get rid of this now. But that's what I'm going to sketch. So again, these are more graph transformations. So again, firstly, we're going to consider e to the x. That's sort of my base function, really. Again, so we have e to the x here. Again, standard graph you need to know, or something like that. If I continue it like that, there we are, something like that. Okay, that's e to the x. Then I'm going to sketch e to the 3x. So again, if let's say f of x is e to the x, then f of 3x is going to be e to the 3x. That's what I need to sketch. Well, then actually, again, if we use the transformation rules, what I do inside the bracket, inside the function, I do the opposite to what I expect. What do I expect? I expect to triple the x coordinates, times them by 3. Well, instead I'm going to divide the x values by 3. So what that means is, again, let's take this point here. Let's say this point is x is 3. That would move to 1. Okay, so then move to here. So it's effectively done by a third. Okay, so this point here moves a third. There we are. And then let's say this point here on the curve would move somewhere there, and then this point on the curve there would move to somewhere there. Okay, so again, the graph, it's going to be sort of squashed. Okay, it's going to be that sort of shape. So if I draw that sort of shape then, y is e to the 3x. Oh, it's going to look something like that. Y is e to the 3x. It's essentially squashed together, okay? But then, of course, we're not sketching e to the 3x, but we're in sketching 7.389 e to the 3x, or technically e squared e to the 3x, right? Because remember, e squared is roughly 7.389. So if we're going to sketch that then, well, we need a multiple of 7.389. So y is going to be, y is now 7.389, lots of e to the 3x. Well, actually, at the end of the day, it's just roughly a multiple 7, right? So actually, we're going to multiply the y values by this amount, by 7.389, or technically by e squared, right? Because e squared is actually the full answer here. But I'm just writing down the decimal to help you visualize what's going on. So then, if I'm going to multiply all the y values by roughly 7.389, roughly 7, again, the graph is going to be even steeper, okay? So it's going to look like this. And actually, first of all, the y-intercept of 1, actually, if I'm multiplying it by e squared, it would then be e squared, so it would be up here, right? Or 7.389 as a decimal. If I were to sketch it, it would look really steep. So it would look something like this. Okay, and that would be y is e squared, 7, technically e squared e to the 3x, or we could say 7.389 roughly as a decimal e to the 3x, right? Whatever helps you visualize that, okay? But that is that graph there. Okay, we're gonna now we're gonna go back to differentiation. So yeah, we need to be comfortable with differentiating exponentials, this e function. So we have firstly y is 5e to the 0.4x. So again, remember that if y is e to the kx, then dy dx is k e to the kx. So we bring the coefficient in front, so the 0.4 comes in front. So that'd be 5 times 0.4. That would be 2. So that'd be 2e to the 0.4x, okay? Then part E, we have y is e to the 3x, add 2e to the x. So again, we can differentiate the term by term. So firstly, if we were to differentiate, e to the 3x, the 3 comes to the front, so that'd be 3e to the 3x. And then 2e to the x, well, e to the x, that's e to the 1x. You just bring 1 to the front, that's just itself. So it's just, again, 2e to the x. Okay, then part F, we have e to the x times e to the x as 1. Now, I actually can't differentiate that the way it is. Like with our power laws, when we use the power rule to differentiate expressions like x cubed and x to the 5, I need to expand the bracket. I need to expand the bracket so I can differentiate it. Okay. Well, firstly, that will go to e to the x times e to the x, right? Okay. Well, how can I simplify this? So, again, if I use my power laws, this is going to be e to the x add x, right? I can bring the powers together by adding them. Well, x add x is 2x. So there we are. Cool. Alternatively, you could have realised this was e to the x squared then. If I'm multiplying e to the x by itself, then because I got the powers in this way, I can multiply the powers together to get 2x that way. Either way, so that would be e to the 2x, and then add e to the x. Okay, if I do e to the x times 1. So e to the x times e to the x is e to the 2x. E to the x times 1 is e to the x. Cool. So then my derivative, if I were to differentiate this, so that's y, then dy dx. But e to the 2x will go to 2e to the 2x, and then e to the x just remains e to the x. Okay, cool. Okay, we're going to finish off with this. Again, it's going to use differentiation. So I'm told the function f of x is e to the 0.2x. Okay, that's my function. I need to show that the tangent at the point 5e goes through the origin. So again, it's talking about tangents. So I'm going to need to differentiate, right? So if this is f of x and the gradient f dash of x, if I differentiate this, well, the 0.2 would go to 0.2 e to the 0.2x. Then that's my gradient function, and the gradient at this point here, the gradient at 5e, well, x is 5. So I'm going to substitute x is 5 into my derivative f dash of x. So therefore f dash of x, which is 5, if I plug 5 in, that'd be 0.2 e to the 0.2 lots of 5. That would be 0.2. But 0.2 times 5 is e to the 1. But that's just e. Okay, so it's 0.2 e. Okay, I'm not gonna convert that as a decimal because I know e is just a number, right? 2.71. I'm gonna leave it in exact form. Okay, I do advise that unless obviously it explicitly says to round it. If you're in the middle of your working out, I wouldn't try and round up in case of rounding error. But that is just 0.2e. Okay, hopefully you're comfortable with that. So that means my gradient m. So again, my tangent, because it's a line, it's y is mx plus c. But I know m is this expression here. It's 0.2e. So y is 0.2ex add c. Okay, so I need a point to substitute into, but I'm told the tangent is at the point here, 5e. So I'm going to substitute 5e. So then y is e. So then 0.2e, x is 5, add c. Then I can do e, and so 0.2 times 5 is just 1. So it's going to be 1e, or just 1, or just e, sorry. So e add c, well that means c is 0 then, right? But that means my equation is simply y is 0.2ex. And then there's no y-intercept. What does that mean then? If the y-intercept is 0, what does that mean? Well, actually then, if it passes through the origin, but then the origin is 0, 0, right? So if I sub 0, 0 in, then that means y0 is going to be 0.2e, lots of 0. Well, 0 equals 0. Well, actually, the equation is satisfied, so the tangent must pass through the origin. Right? So you can do it that way, right? But literally, physically, substituting the origin point in and see that it works. Okay. Alternatively, what I was getting at is because the y-intercept was 0, that means it has to pass through the origin because the y-intercept obviously is when where it crosses the y-axis. But if it passes through 0, it would have to pass through the origin. But you could do it this way instead. Anyway, hopefully you can see it passes through the origin. So that is that question answered, and that's it. So that is exponentials. We will be using this throughout the whole course actually, and we're using e quite a lot in this chapter, and also in year 2 as well. And it's also just a very important number in maths in general. You'll probably, especially if you do it higher on, you'll see it crop up quite a lot. But yeah, that's exponentials. I'll see you next time.